Welcome to this explainer. I am so incredibly excited to have you here today because we're diving into something absolutely wild. We're looking at one of the most critical, complex, and frankly catastrophic ASIL D functional safety failure modes found in modern hybrid dual motor systems. Automotive engineers call it the E06 fault, the thermal and voltage derating logic conflict. Now, this isn't just some minor software bug we're talking about here. This is a massive issue that directly impacts the longitudinal dynamic stability of a vehicle, not to mention the high-voltage electrical safety of the entire DC bus. To really grasp the gravity of this fault, I want you to picture a lethal 1200-volt surge. In a hybrid system, if the control logic fails right at a critical threshold, the motor's back electromotive force can uncontrollably breach its safety limits. And when that happens, it triggers a massive surge exceeding 1200 volts in mere milliseconds. This kind of spike is basically like a lightning strike inside the vehicle. It will instantly destroy the silicon carbide power modules and the film capacitors. Just total devastation. So we really have to ask ourselves, what exactly happens when an electric vehicle's thermal protection violently collides with its voltage protection? Think of this explainer as a high-stakes engineering detective story. We're essentially looking at a scenario where two absolutely vital, life-saving systems, one designed to keep the motor from melting down and the other designed to keep the voltage from blowing up, tragically turn against each other. Let's break down this E6 fault and find the culprit. It all starts at extreme high speeds. To prevent voltage overloads, the system uses a technique called flux weakening, which is injecting a negative direct access current to suppress the voltage. It works, but doing this generates massive heat. If the system starts to overheat, the thermal derating logic steps in, panics, and violently overrides that flux weakening to reduce the current. The magnetic field instantly loses its lock, and boom, uncontrolled power generation just floods the DC bus. All right, let's jump straight into Section 1, Fault Root Cause Analysis. The crucial thing to understand here is that this failure is multidimensional. It's like a perfect storm. First, you have that physical antagonism we just talked about. Second, there's carrier desynchronization. Basically, if the microprocessor's clock phase slips even a little, the dual motor's high-frequency ripples can align. This doubles the voltage ripple and causes the thermal and voltage loops to physically fight for control. Third, we have RTOS, or Real-Time Operating System Priority Inversion. This is where a lower priority temperature reading actually delays the high-speed voltage loop from getting critical updates. And finally, something truly mind-blowing, connector fretting corrosion. Down at the microscopic level, the raw physical vibration of the combustion engine, shaking anywhere from 100 to 1000 hertz, actually causes the low-voltage connector pins to slide back and forth by just 10 to 100 micrometers. This tiny, almost invisible friction creates oxidative debris, which suddenly spikes the electrical resistance. Now to the software, this resistance looks exactly like a massive temperature spike. The engine vibration literally makes the software hallucinate extreme temperatures, which then triggers that catastrophic logic conflict. Moving right along to Section 2, Hardware and Software Collaborative Defense. So how do engineers actually solve this software processing risk? They use a heterogeneous dual-core lockstep architecture. Think of it as two independent agents working side by side. Core 0 is the doer. It's executing all the highly complex, high-speed motor control and derating limits. Core 1, on the other hand, is the checker. It operates totally independently, constantly looking at Core 0's math and checking it against the unbreakable laws of physics, like stator flux conservation. If the doer makes a mistake and requests a dangerous power spike, the checker can step in and violently cut the power path in under 100 microseconds. But here's the catch. You can't just cut the power at 12,000 RPM. That would cause absolute chaos and snap the drive shafts. So the system relies on an adaptive fallback strategy. Level 1 gently ramps down the torque at 500 Newton meters per second, nice and smooth. But if the crisis is severe, like an uncontrolled voltage spike, Level 2 kicks in. At high speeds, the system executes a stepwise active short circuit. This safely absorbs the massive regenerative energy directly into the motor's stator coils as heat, and it perfectly clamps the voltage at a safe 720 volts. That brings us to Section 3, Key Design Preventions. Remember that microscopic fretting from engine vibrations we were talking about earlier? Engineers solve this by completely upgrading the bill of materials. They mandate 100% gold-plated pins for all low-voltage signal terminals. Because gold doesn't oxidize, even if it vibrates, the contact resistance stays at a microscopic 1 to 3 milliohms. Then, they pair this with ultra-stable Class 1 C0G ceramic capacitors. This combination completely eliminates the hardware hallucination issue, regardless of intense heat or vibration. Now, these design defenses have to be holistic. On the software side, they deploy a dynamic priority derating limiter. This algorithm explicitly hardcodes flux weakening as the absolute priority. This guarantees that thermal limits can never ever fatally override voltage protection. They also add advanced adaptive observers to keep the torque estimation highly accurate even up at 150 degrees Celsius. Plus, they implement a synchronized hardware clock source that limits phase timing errors to less than half a degree. That completely kills the ripple interference bug. Next up, Section 4. Key process controls. So, how do these brilliant designs survive mass production? The manufacturing controls are extreme. On the assembly line, every single unit goes through end-of-line automated fault injection. They spin the motor up to 12,000 RPM and intentionally inject a false overheating signal just to make sure the software prioritizes voltage control correctly. They also apply a specialized anti-fretting fluorosilicone gel using UV vision-guided robots. And to top it off, they lock the safety calibration parameters using cryptographic SHA-256 hashing so no one can accidentally overwrite those safety bounds. This all requires totally uncompromising quality standards. Every single microcontroller goes through 100% 3D X-ray screening. Why? To check the microscopic solder balls sitting underneath the chips. The total voiding rate, which is the amount of empty air bubbles trapped inside the solder, must be under 5%, and a single solder ball cannot have a void larger than 1%. If a void is too big, years of engine vibration will eventually crack that solder joint, disconnect a safety sensor, and trigger our dreaded E06 conflict right out on the highway. Finally, let's look at Section 5, Extreme Production Validation. This right here is a literal torture test scorecard. They bake the system at 105 degrees Celsius while it's running at maximum speed. They violently shake it on 3 axes at 35 meters per second squared while rapidly cycling temperatures from -40 to +125 degrees. And they run hardware-in-the-loop simulations where they literally simulate the battery disconnecting at full load. Through all of this chaos, the system must never lose voltage control, it must never drop a signal for more than a single microsecond, and it must securely clamp all voltage spikes. So the crucial point to take away from all of this comes down to one terrifyingly short metric: 60 milliseconds. This is the FTTI, or the fault-tolerant time interval. From the exact moment a microscopic vibration causes a sensor to glitch, to the moment the dual-core checker realizes the motor is demanding too much power, to the moment the safety logic violently shorts the motor phases to absorb that 1200-volt surge, everything we discussed today must flawlessly execute in less than the blink of an eye. Because if it takes 61 milliseconds, the inverter explodes. It really makes you think, doesn't it? We just hop into our cars, press the accelerator, and have absolutely no idea about these incredible, high-stakes detective stories and engineering battles being fought in milliseconds right under our seats. As hybrid and EV architectures continue to push toward even higher RPMs and ever more extreme voltages, how will these invisible software wars evolve next? I hope this explainer gave you a real appreciation for the sheer mastery of modern automotive engineering. Keep wondering, keep learning, and I'll see you in the next explainer.